Let's try this again. Happy Sunday, SuperCon. I need a little more. I'm sorry. That's better. Thank you very much. I got to make sure you're awake. Again, Saturday was a long night for some of us. If anyone's hungover and this is a little abrasive, then you should have known better and you should have drank less. So I got nothing for you here. We're a little late getting started, but hopefully that just means that you're extra ready for our next speaker, who is an electrical engineer who is passionate about sustainable technology and is also a personal friend of mine. Just saying that because I'm proud, not for any other reason. She has contributed to diverse climate tech initiatives, such as robotics for sustainable farming and electrification of gas-powered tools and vehicles. She's also a dedicated maker and a STEAM outreach creator, and just all around a really cool human. So, all of this being said, please put your hands together to welcome to the Hackaday Super Conference stage, Ayesha, of course, I'm gonna stumble on it the second I need it to matter, Ayesha Iftiqhar-Wilson.
Do I just pick this up? Okay. I haven't done this, so let's bear with me. Ali did a great introduction, so I think I should just leave. I'm here to talk about environmentally friendly electronics. It's something I'm very passionate about and excited to talk about, so thank you all for being here. This was a result of a panic attack I had about e-waste, so this is very therapeutic. So my name's Ayesha. I have a lot of climate anxiety and some electrical engineering skills, so I decided to make a career out of it, because that seemed a healthy alternative. I've worked on things like IoT-connected sensors that are used in dishwashers to monitor water and energy consumption. Worked on Ryobi power tools. You've probably seen these green tools everywhere. So worked on the electrification of those to move away from gas-powered tools so they're battery-powered and have brushless DC motors, which are more efficient. So you smell gas and not, sorry, you smell grass and not gas. I've worked on strawberry harvesting robots that are used for sustainable farming. These are used in hydroponic grows so that we're using less water when we're growing food. And we also did cool things like adding UV lights to disinfect the plants instead of using chemical pesticides. So that was a really cool project. And I was the lead electrical engineer on designing the very first all-electric RV, which is completely solar-powered and battery-powered. I designed the first few prototypes, wasn't there for manufacturing, but really proud of that. And recently, I've been working on air quality monitoring sensors to measure CO2, methane, and all these pollutants. These are used by government and scientists all over the world and a lot of local cities as well. Really proud of the work I've gotten to do so far. I also really like PCBs, as does everyone else in this conference, I'm sure. I use all my PCB work to get more people involved, especially underrepresented communities involved in engineering, and teach them how to solder and program, and I make a lot of my work inspired by nature. And as much as I love using electronics to make all these cool things and solutions that help the world, I came across this statistic that e-waste is one of the world's fastest growing solid waste stream, and I was kind of sad. So this is what we're going to be talking about for the rest of the talk. And as engineers, this is how we're going to structure this talk. We are going to talk about the problem, understand the magnitude of the problem. Then we'll talk about like high-level design strategies, which sounds very interesting, I know. And then we're going to talk about more specifics about what we can do as electronics designers of how to potentially mitigate e-waste. Okay, so let's understand what this means. Fastest growing solid waste stream. In 2022, we created, as humans, 62 million metric tons of e-waste. Now, I don't know what that means, so maybe close your eyes and visualize this with me. That means 125,000 jumbo jets. That means 4,500 Eiffel Towers lined up covering all of Manhattan. That's a lot. How did we do this? Uh, okay, so, but that's only 2% of the solid waste we are creating, but that contributes 70% of the toxins we are adding. It's kind of scary. What's US's contribution in this? This is about 11.45% that we are contributing, even though we are only making 4% of the world's population. And while e-waste is growing so fast, since 2010, the rate of growth of e-waste is 5 times faster than our recycling capabilities currently. So we don't have the infrastructure to support this to begin with. And we haven't been doing the best job recycling anyway, because we've only been, there's only been 22.3% of e-waste being collected correctly. Everything else is ending up in our landfills. So what's the economics of this? That means we are throwing away $91 billion worth of things that we could be using. Most of this is in precious metals, such as copper, gold, and iron that are used in electronics. And not only are we throwing this away, we are still continuing to extract this from the earth. And if we didn't do this, if we did this properly, that would have resulted in the equivalent of carbon emissions that would have been reduced if we took away 20 million cars off the road. Now take all this with a grain of salt, because obviously there are nuances in this, but it's a good picture for us to analyze. The other thing is, this is what, we've seen this periodic table, this is what it looks like. All the orange tiles on here, which is like most of the periodic table, that's all the metals that are materials or elements that are used in electronics. And everything that's highlighted in blue, red, and orange are at a varying degree going to be scarce in the near future. So we're not going to have stuff to make all the cool things we want to make. So yeah, that's sufficiently horrifying. So that's the problem. We understand the problem. We are engineers, though. We like talking about solutions. So let's talk about solutions. For solutions, when I was doing my research, I don't like design practices and certifications, but I went down the rabbit hole for y'all. And I came across 2 main design principles. Oh, sorry, I skipped ahead. The solution lies between policymakers and consumers, policymakers, designers, and consumers. I'm not going to talk about the rest of it, but we are designers, that's what we're going to talk about. Cool. Sustainable designing engineering is one of the design principles I came across heavily when I was looking this up. There's no single source of origin for this, but this has been like the result of various academic researchers and environmentalists and economists talking about this. And it's loosely based on ISO 16000 directive, which is a directive for industries and companies to follow to reduce the environmental impact. And I distilled down all the research I did into 3 key points that I learned from it. The first one is life cycle assessment. So when you're doing, or when we're all doing product design, this is where we go through each step of a product design and think of everything from supply chain to production to testing to production to sending, and like how that's going to end up in at the end of like your product cycle. We're going to go through all these steps and have data of like what the environmental impact of each of this step is, so we can identify what the biggest environmental impact sources are, and then try to reduce it. So that's one strategy that this SDE recommends. The other is circular economy. This is something that, yes, we've been talking about recently, and it's very exciting, because previously we've been talking about economy and products in a linear way. We keep hearing the term cradle to grave over and over again. This introduces more of a cradle to cradle kind of a design process. And it introduces things like reusing things, repairing things, recycling things, so that we can make sure like the materials we are extracting gets recirculated back into making more things, which is awesome. And it also has economic benefits, which is also really cool. Resource efficiency is the other part of it, so making sure all the resources that we're using are extracted in a environmentally impactful way, as well as the resources that we're using, we are making the most of it. And as engineers, we love that. We love making the most out of our materials. So this is kind of a loser concept, but there is another design concept called design for environment. This is defined by EPA. EPA, if you all are aware of it or not aware of it, it's Environmental Protection Agency that was formed in the US government in 1970s. And they came up with DFE in the early 90s when they were trying to make a safer choice program for consumers. So if you've seen products with a safer choice label on it, they've gone through this process. And this is mainly for chemicals, but we can use this similar concepts for electronics. Similarly, I've distilled it down into a few points. First is environmental processing and manufacturing. Similar to SDE, this is where we are making sure like each processes, including like our suppliers, our production houses that we're using, they all are doing things in an efficient way. Next is eco-friendly packaging. This is making sure like all our packaging is using materials that are least impactful on the environment, as well as making sure they're recyclable. So think of things like cardboard and making sure everything's labeled, because that's very important in recycling. Then disposal and reuse is another thing, to make sure things are easy to disassemble, easy to reuse. Again, labeling is a huge part of it to make sure things can be reused. And then making energy efficient choices. I'm going to talk a little more detail about energy efficiency, so I'm going to skip that a little bit now. And I like DFE specifically because as product engineers, we do DFM and DFT, design for manufacturing and design for testability, and we follow certain steps. This kind of follows that kind of structure already, so it's easier to implement that in our design. Although DFE does certify safer choice products for chemicals, it doesn't do that for electronics. But there are other certifications. I'm not going to get into detail of it, but this is kind of the summary. There's something called Electronic Product Environmental Assessment Tool, EPEAT, which is done by Global Electronic Council, and it's usually for bigger companies. They do like bronze, silver, gold levels for it, and it's pretty rigorous, it's pretty expensive, but they make sure that all the products are following all the guidelines. Energy Star is something you all have probably seen on like dishwashers and laundry machines, etc. This is a very important thing for consumer electronics that use a lot of energy. So EPA does this, and you can test your product from EPA recognized labs to get the certification and have your products, especially when they're in the larger scale, do this. This is also moderately expensive and tedious. So you kind of have to decide if you want to do it or not, but both these certifications have their guidelines available, so you can still follow them and do it regardless. RoHS is something probably most people are aware of, reduction of hazardous substances. This is a EU directive, and it absolutely needs to be done if you're trying to sell in the EU. And this is something that makes sure that you're not putting harmful substances in your electronics, like lead and mercury, etc. And this is more of like making sure your supply chain is using clean products. And it's self-certified, or you can use a third-party certification, so most people do RoHS. But you can still follow them, even if you don't do certifications. Okay, so the summary of all those documentation is this. Do things deliberately, and make sure you're not breaking things and you're fixing things. So that was like the high-level design. As circuit designers, I wanted to distill it down into 4 main slides. So first is material and component optimization. So when you're designing, think of how you can use the least amount of parts and make sure those parts are RoHS compliant. Lesser the parts, lesser things that can fail, lesser things you have to source, just overall more efficient. Power duration. Who does power duration very religiously? Good. Who knows what power durations are? Okay, let's talk about this. This is very exciting. So if you look at component data sheets, you see voltage and current maximum ratings for everything, right? And what do we want to do? We're like, oh, if it's going to be a MOSFET for 20 volts, 10 amps. We are like, let's run it at 20 volts, 10 amps. That's going to reduce the life cycle of your component. If you reduce it by half even, that's going to extend the lifetime of your component by anywhere from 2 to 10 times, depending on how much you're derating it, because you're not stressing out the components that much. So that already extends the life cycle of your product. Using socket type connectors for things that fail very easily, so they're replaceable, so you're not replacing your entire board. That's another strategy that's pretty useful. And life cycle assessment, again, making sure you're thinking of every stage of your product design is helpful. Protection and durability. Things fail, we know this, so let's protect it from that. Using conformal coating and IP enclosures reduces the chances of humidity and dust coming in, which is a horrible thing for electronics. There are actually some very interesting case studies done of airplanes breaking because there was dust and moisture on circuit boards. Terrifying, but that can be protected. Battery selection is something I want to spend a few times on because we all work with batteries. Okay, I know there are different sources. I'm gonna focus on 3 types. Let's do lithium ion, because we use that a lot. Nickel metal hydride, and just your regular AA cells, which I'm blanking on the alkaline batteries. Who thinks alkaline batteries are overall better for the environment? Pretty much no one? Okay. Okay, a few people, okay. Lithium ion. More people. Nickel metal hydride. About equal people, okay. Huh? Lithium iron phosphate, okay. Let's do lithium iron phosphate too. Okay, let's start with alkaline. That's your AA cell batteries. Single use, not so great. They have smaller density packing, so they're better for small devices that don't have a lot of current demands. So that's the application. They do not get recycled very well because the materials in those batteries are not very valuable, so no one's trying to recycle them. A lot of places don't. So they end up in the trash. But when they end up in the trash, they don't really they have harmful substances, but they're not as harmful as some of the other substances. So they can end up in the trash and be less harmful than some of the other batteries. So they have their place in the world. Lithium-ion batteries, on the other hand, they have a lot more capacity to hold current, and they're lighter and they're better for higher power applications. They are horrible to source because they have a very large environmental impact when you're mining them, and the systems are not in place to recycle them very well. So they are not also that great. Nickel metal hydride kind of sits in between because you can reuse them, and they're moderately okay to extract. They're actually pretty good for recycling. There are systems in place to recycle them pretty efficiently in air quotes. So that they are better. And their current capacity is somewhere in the middle of these 2 extremes. So they're pretty good for a lot of applications, but they're a little heavier than maybe lithium ion. Lithium phosphate, I'm thinking it's going to be similar to lithium ion. I didn't do my research on that, but I will get back to you. So there's always trade-offs in design. It's good to go through what your application needs and follow that. Failure mode analysis is another way to find out how things break and try to not break them. Who knows how ceramic capacitors break on PCBs? Okay, let's say, do they fail open? Who thinks they fail open? Raise their hands. Do they fail close? Raise your hand. Yeah, they fail in both ways. That's the interesting part. So if they endure stress, they fail open and they crack. And then if moisture gets in, they short. Yeah. So doing things like failure mode analysis helps you know if you want your power to be shorting to the ground. For example, if you're using decoupling capacitors, and try to prevent that. So yeah, that's helpful. Resettable fuses are helpful. Fuses in general are helpful. I like resettable fuses. Preference is a thing, just so you can prolong your life. Predictive maintenance is good, knowing when things might break so you can inform your consumer to maintain it to extend your life is another good strategy. Last two, I promise, I'll be fast. Energy efficiency and design, making sure you're using things like switching regulators instead of LDOs to improve your power efficiency, for example. Underdriving your components to extend their life cycle again, lifespan again, and also heat management, that helps. Eco-friendly wiring, make sure like you know what coatings you're using, how they can be recycled, helpful. And then we are thinking about end of life, because we don't like to think that our products are going to die. We want them to live forever, but they do die. So how do we want to make the most of it? We are going to think of how do we want to disassemble it, so make sure we are doing the right things to make it easy to disassemble. Using things like standard screws is one thing that adds part. You can use snap enclosures, snap fit parts to make it a little easy, has its pros and cons. Adhesives are generally not that great, so maybe don't use them. Labeling things is like probably the most important things. If you can take away one thing, maybe that. Make sure you label things so when they're recycling it, they can sort it easily. Designing with modularity in mind, so if something breaks, you can replace it and continue to use the product, or they can have a second life is important. Using renewable materials is another good thing. Okay, ending in fun part of this. So when circuit boards die, they can have a second life still. These are a few cool examples I found, including Alex's dual thief circuit that uses old batteries to suck the last bit of juice out of the batteries to light an LED, for example. It's a great use. It's a boost circuit. A lot of people have been using fashion and art to reuse old PCBs to make cool things. I didn't include this, but there have been a lot of, like a huge moment in hacking toys and reusing parts from toys to make new products, which is also really cool. And vapes is another thing people have been trying to get batteries out of and reuse and do cool things. So a lot of fun applications that we can still use instead of just throwing away our electronics. That's all I got. Thank you. This is where you can find me. I have more stuff here if you want to learn more. Cool. Yes, you have a question.
Yeah, I do have a question.
Yeah.
Sorry. I had a couple slides back that this one right here, conformal coating and IP enclosures. So this is something that you can use that extends the lifespan of components, but it also reduces the ability to recycle them and take them apart at the end. So how do you balance those two things?
That is very true, and this also makes it hard to repair. I guess you need to find the balance of like how long do you want your boat to live. The goal is to reduce the trash already, and if you can extend the life cycle, do that. If it's something that needs to be changed quickly, then maybe that's fine. IP enclosures are the better option then. You don't have to use conformal coating in that case. Yeah. Cool. How am I doing on time? Am I supposed to leave? Do I have time for questions? There's one more question. 2 minutes. 2 minutes.
I love the talk. Thank you so much. I feel like a lot of engineers, a lot of us really care about making our electronics more sustainable. But when we work with our clients or when we work with our employers, there's a lot of pushback. So how would you advise us to push against that pushback, really?
Yeah. One thing I found useful, because I struggle with that, is that companies are trying to hire, and more people care about this stuff. So saying things like, hey, if we follow these guidelines and if you're actually doing things that are good for the environment, maybe you can hire better people. Yeah. Yes.
My question is really, if you think like maybe 10 years into the future, do you think that a lot of the products will
I hope so, because we need to do this. There is no alternate right now, and it is up to the bigger companies to kind of take the lead. And I know like there's a lot of greenwashing where people claim they're doing stuff and they're not. So I think it does come to a little bit of individual pushback from like maybe people and pushing more on that. And I think lawmaking, policymakers is the other key ingredient there. So vote responsibly and ask your policymakers to vote on these things. Yeah.
On a similar note, people are working towards multiple like biodegradable substrates for PCBs and stuff, which I think is awesome. As someone who's into PCBs and makes beautiful PCB art, I was wondering if you looked into this at all, and also, would you like to collaborate?
Yes. I have not looked into it, but I'm very curious for sure. And I guess all of us can look into it because we all like making PCBs. Yeah. Any other questions? Okay, yes.
You talked about recycling, like enclosure plastics and stuff, and it's important to label it so you can recycle it later. I was always curious, like, do people on the recycling line actually like sit there and look for the recycling number and then sort it correctly, or?
Yeah, so I've been to one recycling place so far. I don't know what the general thing is, but they do. People do actually sort it. And there is a lot more of like machine level stuff that's happening. They're using machine vision to like recycle plastics responsibly. So that's why labels, again, are important for that reason.
I can actually answer that question
Yeah.
a little bit. Fun fact, most plastics have a different, they float differently in different materials. So for the most part, the first sorting is usually they throw them in a few different materials, waters, oils, various things, and they will float differently, and they can actually sort them massively that way. But like the human bit is a factor, but it's usually after they do this initial sorting, which is surprisingly low tech, but works really well.
The other thing, when I did the recycling thing, they're using fans too, which I don't know if it's for this particular case, blowing fans and recycling things based on like how they separate on weight. They're coming up with cool things. Okay, that's all from me. Bye.